going to explain about limitations of algorithmic power. Okay, so that means the topics I'm going to cover here in this video is what do you mean by algorithmic power, and what do you mean by this limitation of algorithmic power, and what do you mean by lower bound, and how to find the lower bound by using different types. Okay, these are the topics what I'm going to cover in this my video. Now, first of all, why we are writing the algorithm? So whenever we are having some problem, so to solve the problem, first we are designing some solution in the form of pseudocode, and that is nothing but the algorithm. Okay, so that means for the given problem, first we will write the algorithm. Okay, so that we know that. Okay, so for the given problem, so we are going to write some algorithm. This is my algorithm. Now, once we design the algorithm or once we write the algorithm, next step is what we are doing the analysis of the algorithm. So why we do the analysis of the algorithm? So we do the analysis of the algorithm to know what? To know the efficiency of the algorithm. That means to know the what? Efficiency, or we can say to know the performance of the algorithm. To know the efficiency or performance, that performance or efficiency only we are calling it as power. So that's what is power. Okay, so that means to know the algorithmic power, we are doing the analysis. That means once we do analysis, we can say this so and so algorithm is taking this much of time in best case or in worst case. That we are telling. That means this is the power of the algorithm, or this is the performance of the algorithm. So here power means not the physical power. Here power is in terms of either the performance of the algorithm or efficiency of the algorithm. So that is what the algorithmic power. So hope you people know what you mean by algorithmic power. Okay. So again, summary is once we write the algorithm, so then we are doing analysis of the algorithm to know the efficiency of the algorithm or performance of the algorithm, or we can say power of the algorithm. And every algorithm has its some power, right? And similarly, every algorithm's power is also having some disadvantage. That means we say, suppose take algorithm bubble sort. Bubble sort is used to sort the given set of elements, and it is taking n square time. That is the power of the bubble sort. Power of the, that means efficiency or performance or power of the bubble sort is n square. That is the power. That is it. But that is good. No, that is having some disadvantage because it is taking too much of time. So that means similarly every algorithm has its own power, and as well as every algorithm is also having some disadvantages. That disadvantages of that algorithm power we call as the limitations of algorithmic power. Okay, so every algorithm is having some advantages and as well as disadvantages. The disadvantage of the algorithmic power, we call it as what? Limitation of algorithmic power. Okay, so hope we know the second topic also. Okay, now let us see, first of all, why we need to find the limitation of the algorithmic power. Now, let us take a simple example of a student. Assume a student scored some marks in the exam. Assume he scored, for example, say he scored some 62% he scored in the exam. Now, assume same another student in the same class, he also scored some say 94%. Now, what we can say, this student still has to improve when compared to this one. Okay, that is the information. That means once I know the power of the, so that means say, so this is the marks or percentage of one student, this is the percentage of another student, both are belongs to the same class. So when I compare these two performance of these two students, I can say this student has to improve a lot. This is the information we get. Okay, so similarly, whenever we do analysis, we are finding the efficiency of the algorithm or performance of the algorithm or power of the algorithm. Now, till now, how we are finding this efficiency? So how to find the efficiency? There are two types. Okay, so first way of finding the efficiency is as using, so we are using what? Asymptotic notations. So whatever we used, asymptotic notations. Okay, for example, so that is what big O or big omega, big theta. This is the method what we till now we know. Okay, so this is one way of finding the efficiency of the algorithm, but it will says just efficiency of so and so algorithm in worst case is so and so. Bubble sort algorithm time complexity is n square in average case. That's it. Okay, linear search best case time complexity is 1. Okay, binary search time complexity is log n. That it will say. That's it. Okay, but I don't know whether where it stands, because here I'm not comparing with anyone. Okay, so here what I'm doing, so but now the second method, so here what I will do, here I will compare the what? I will compare the efficiency of one algorithm with another algorithm of what? Same type, same problem type. That is the main thing. Okay, so that means here what is the second way of finding the efficiency is I will find the efficiency of one algorithm and I'll compare the algorithm of another algorithm of the same problem type. Exactly like this. Here in this case what I am doing, in this case just I find out the efficiency, that's it. I find out this person efficiency, I find out, that's it. But in this case what I will do, after finding the efficiency of this student, I am comparing with another student of the same problem, of the same class. Now I came to know there is a lot of room is there to improve the student. That is the information I will get from this. That I won't get from here. Now for example, let us take again. So bubble sort. So bubble sort will take n square time complexity. Bubble sort will take. But now this is what we did here, that's it. But now what I will do, I am comparing the efficiency of bubble sort algorithm with another sorting algorithm. Both are sorting algorithm, both are same time. So I will compare with the merge sort. When I compare with merge sort time complexity is n log n. When I compare these two, this is taking more time. That means it is slower. This is faster. That means there is a lot of room is there to improve. So I came to know that this we need to improve. This is what the information I got. So this is from this method. Now similarly, suppose for example you can say, so why you need to compare bubble sort with merge sort? Now I'll compare with another sorting method. So that is quick sort. The quick sort time complexity is also n log n. When I compare these two, I came to know that this and this is almost same and both are tightly coupled. Both are tightly coupled means there is no room or there is no space between these two. That means we cannot say this algorithm has to improve like this. For example, suppose say this person is, okay, one person is taking 94%, another person is got 93.9%. Now I cannot say you have to improve a lot. No, it's not possible. This is tightly coupled. Okay, so when I compare the efficiency of one algorithm with another algorithm, we will came to know the information about whether one can be improved or not. So in this case, yes, exactly. Here we need to improve this. But when I compare these two, no, there is not possible to, or there is no need to improve this one. Because almost same. So this is what we came to know when we compare the efficiency of one algorithm with another algorithm of the same problem type. Okay. So we know what do you mean by algorithmic power, what is the limitation of algorithmic power, and why we need to do that comparison. Now, how to find the efficiency of an algorithm, this is one way. Another way is by finding the lower bound of an algorithm. Another method is by finding the lower bound of an algorithm. Now what do you mean by lower bound? Lower bound is nothing but the estimation of minimum amount of time taken to solve the given problem. That means in order to solve any one problem, you have to put some effort. That minimum effort, how much we need to put, so and so we have to solve the problem. So that estimation of minimum amount of work to be put in order to solve the problem is called lower bound. So hope we know what you mean by lower bound also. Okay. Now, for example, see, assume now a student has to appear for the exam. Assume a student has to score something. We are not telling how much. We have to score something. Now, some student will put more effort. Okay, but some students are the smart students. They are very good in academics, with studies. They are having very good memory, very good grasping power. They will put minimum effort but score more marks. But there are some students are there. They'll put more effort but they'll get less sum. So that means now, so this person how much put the effort in order to get this much marks, or this person how much they put. So that is the lower bound of this case. So the lower bound of an algorithm is nothing but estimation of minimum amount of work to be done in order to solve the problem. That is what you mean by lower bound. Now, in order to know the lower bound of any algorithm, we are having 4 types. So to know the lower bound or to find the lower bound, we are having 4 types. One is trivial lower bound, second one is information theoretic argument, third one is adversary argument, fourth one is problem reduction. So these are the 4 methods to find the lower bound of any algorithm. Now let us see one by one how these methods are used to find the lower bound. Okay, now first one, trivial lower bound. In the trivial lower bound, so we know that once we write any algorithm, so that algorithm or this program alone doesn't give the output. Suppose I have written a program. Assume I have written the program to add 5 elements. When I written the program to add 5 elements, so I written the program. Alone it gives the output? Never. Now I need to pass some inputs. How many input? The 5 numbers I have to give. Now my program or my algorithm take these 5 inputs and do some operation on this 5 input and then produces one output. Similarly, if you take sorting elements, assume I have done a sorting algorithm. Okay, so that our algorithm has to take the elements which I want to sort and it has to read all the elements and then it has to produce the output. So the problems in which our algorithm has to read all the inputs and then it do some operation on that inputs and produces the output, and that how much time it spends to read all the inputs, to do some operation on that inputs and then the time to produce the output, all this total time is nothing but the lower bound. So in the trivial lower bound of an algorithm is calculated by the amount of time taken to receive the input, all the inputs, to process the inputs and to produce the output. Altogether time is nothing but the lower bound found by the trivial lower bound. Now, so what are the types of problems we can solve, or for what are all the type of problems we can find lower bound using this method is whichever the problem in which we need to read all the inputs. For example, array of sum of array elements. That means given an array, we need to find all the array elements. Array uniqueness problem. Or we need to find combination of some numbers, all combination of some digits. Or we get to find sorting the numbers. Okay, they for such are matrix multiplication, matrix addition. So for all these type of problems we can apply. For what kind of problems we cannot apply this one is, for example, linear search. In the linear search, what I am doing, given set of elements, I am comparing the key element in the first element. If the first element only we found, we stop searching. Remaining elements I am not at all checking. Similarly, in the binary search, always we are finding either in the first half or in the second half. There, all the inputs we are not reading. For that type of problems, we are not applying this trivial lower bound. Okay, in trivial lower bound, we are finding the lower bound by calculating the total time taken to read all the inputs, to process the input, to produce the output. Okay, so that's how we are finding the lower bound in trivial lower bounds. Okay, so the first one is over. Now, the second one is information theoretic arguments. So that means here only it will says algorithm generates some information based on some theory. So based on some theory, how much information our algorithm generates, from that information we'll find the lower bound of an algorithm, the time taken. Okay, for example, assume I have written a program. I have written an algorithm or program Okay, so for do sum operation. Now my algorithm will generate some extra information. The extra information generated by algorithm, from that I am finding the lower bound of an algorithm. Now let's take one simple example. Okay, guessing a number. Assume you people guessed one number. Okay, assume we have people guess the number. Okay, let us say I don't know. You guess one number, x is equal to something that I don't know. For example, assume you have guessed. Now what I will do, that means our algorithm should keep asking the questions and it should get the answer. Now our algorithm should keep asking the questions like yes or no question. That means for the question, answer is either yes or no. So such type of questions only this keep asking. Now for each question, so you people has to say yes or no answer. That means the user has to tell it. So algorithm will ask the question, user has to say yes or no. From that yes or no information, it will find out what the number it is guessing. For example, assume some person has guessed some number. Let us take some between some 1 to say 25, the number guessed. Now I will ask the questions like this. Yes. Now let us say the number, now I am asking in the terms of binary. Okay. So assume there are 4 bits are there. 1, 2, 3, 4. 25 means 5 bits. Let us say 50. Now this is my LSB, least significant bit. This is my MSB. Now I will ask, now that is algorithm will ask whether LSB is 0. That is the first question asked by the algorithm. Now answer should be what? Either yes or no. Now assume LSB is 0. That is the question. First question. LSB is 0. This is the question. Now suppose if the answer is yes, LSB is 0, yes, that means this is 0. Now the second question. MSB is 1. The answer is, suppose answer is yes, that means MSB is 1, yes, means MSB is 1. Similarly, now second LSB is 1. Suppose answer say no. No means not 1 means what? It is 0. Now again say, so then second MSB is 0. Now again answer is no. Not 0 means what? 1. Now we get the middle number. The middle number is 1. Suppose answer says 0, no. Okay, suppose for example, middle number is 0. Answer says again no, means this is 1. That means what? The number is guessed is what? 28. The number is guessed is what? 28. So this we convert into decimal at 28. So this is the information. See, for each question, LSB is 0, yes. MSB is 1, yes. Second LSB is 1, second LSB is 1, no. Second MSB is 0, no. Now the middle number is 0, no. So that means this is the information generated by our algorithm. So from this information generated, from this theory, I find out the solution. That is what the information theoretic argument. Okay, so this is, that means now the time taken to generate all the theoretic questions from that answer, then from that information you need to construct the solution. So that is the time taken and that will be the lower bound. This is how this method find the lower bound of an algorithm. Next, adversary argument. It is almost same as this one only, but in adversary argument what it will make, now our algorithm will, so it is not as unnecessary questions. Okay, but in adversary argument it will ask, instead of getting the answer in the straight away, it will ask too many questions and it will come from the longest path, from the large set of input to narrow down to a single question. And finally it has to get the solution after asking so many questions. For example, assume, again guessing. Now here not the guessing the number only. Now suppose assume you have to guess the number, say between say 1 to say 200. Now the questions will be whether the number is lesser than 100. If it is yes, means number is between 1 to 100. Now whether the number is even number, yes, that means 2, 4, 8. Again, whether the number is divisible by 5, Whether the number is between the range 10 to 20 or whether the number is between 35 to 45, like that we have to ask too many question sets. From this too many question sets, we should keep ask one by one again. Finally, for the final question, get the answer. So that amount of time taken to reduce the large set of inputs to single at the longest path is nothing but the lower bound of this one. Okay, this is how to find out the lower bound from this adversary argument. Okay, now the last one, the problem reduction. So in the problem reduction, as the name itself indicates, assume I want to find out the lower bound of one algorithm. Assume given a problem, some problem is given, say problem A. Now for this problem, I need to write the algorithm. I need to solve. But assume I don't know how to solve the problem. But I know another problem. Another problem I know, that is B. This is entirely different problem when compared to this problem. These two are not the same problem. Both are two different problems. But I know how to solve this problem. I know how to write the algorithm for this. I know only this one. So I will write the algorithm for this one and I will find the lower bound of this algorithm only. And whatever the lower bound of this algorithm, that will be converted into this problem. That means, summary, given one problem that I don't know how to solve that problem, but I know another different problem. Now I will convert my problem into another known problem of another type, and for that algorithm I will write the algorithm and then find the lower bound of this algorithm. Whatever the lower bound of this, the same thing is what the problem. For this problem, lower bound. So how? Let us take one example. So assume, given the problem, say array uniqueness. Array uniqueness problem. What do you mean by array uniqueness? Given some array of elements. In that array of elements, whether all the numbers are unique or not, that I need to check. Whether all the numbers are different or not, I need to check. But assume I don't know this. But I know one more problem called minimum spanning tree, construction of minimum spanning tree. Both are completely different type of problems. So I know how to construct the minimum spanning tree using Prim's algorithm or using Crisp algorithm. I know that. Now what I will do, I will solve the problem and I will write the algorithm and I will find out. So for how? Because assume now the values given, okay, so assume 5, 7, 3, 4, 6. So these are the array elements given. I need to check all these elements are unique or not. I don't know. So what I will do, I will convert these values into Cartesian products, that is 0, 5, 0, 7, 0, 3, 0, 4 and 0, 6. I convert it into Cartesian. Now what I will do, so let us say this is 0, this is 2, this is 4, this is 6, this is 8. Now what I will do, now I will draw the graph. Because the edges, minimum span tree means what? Edges, tree, nodes and edges. Okay. Now first value is 5. So first value 5 means it comes in between this one. So here 5. This is the first number. Next number 0 to 7. So 7 means at least assume come in between 6 and 8. Okay, this is 7. Next to 3 comes here in between. Let us take this is 3. This is 4. Exactly, this is 4. Now this is 4. And this is 6. So it comes here 6. Now I'll check length of all these edges. Now length of all these lines are different. So length of all these lines are different means all the numbers are different. So that means this is how I find. See, suppose, assume any one number. Assume this is also, instead of this is also 4. Okay. Now this is also 4. Now these two lines are in the same length. So when there are two lines are same length, I can say two numbers are same, that is equal numbers are there, that means the array is not unique. So this is how we convert one problem into another problem of known type, and whatever the lower bound of that will be the lower bound of this algorithm. So this is what we mean the problem reduction. Okay. So hope it is clear. So we have discussed what do you mean by algorithmic power, what do you mean by the limitations of algorithmic power, what do you mean by lower bound, and what are the different types of find in the lower bound, and we discussed all 4 different types of find in the lower bound with an examples. Okay, hope you people understood. So if you have any questions, please write it in the comments. Thank you. Thanks for watching.